Hello there, and welcome to the Sleepy Space Channel. Here is a sobering truth about the largest stars in the universe. To become so vast, a star must first begin to die. The greatest stars are not in their prime. They are swollen into enormity by old age, burning through their final fuel, shedding themselves slowly into the dark, and they will last only a brief moment against the long ages of the cosmos. Tonight we will climb the whole scale of the stars, from the small and patient to these vast and fading giants, and learn that the largest suns are also among the most fleeting. If you find these slow explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. The question we cannot quite hold. There is a question that sounds simple until you sit with it. How big is the largest star in the universe? It seems like the kind of question that should have a single, clean answer, a single name, a single number written somewhere and agreed upon. And yet the closer we move toward it, the stranger and softer it becomes. Tonight we are going to climb slowly toward that answer, one careful step at a time, and we are going to find that the summit is wider and gentler and less certain than we expected. Before we begin the climb, there is something we need to understand about stars. A star is not a solid thing. It has no shoreline, no crust, no clean outer wall where it stops and space begins. A star is a vast ball of glowing gas, mostly hydrogen and helium, held together by the inward pull of its own gravity and held up by the outward push of the heat and the light pouring from its core. The two forces balance, and in that balance, a star simply burns, quietly, for a very long time. Because it is made of gas, a star fades at its edge, rather than ending. The gas grows thinner and thinner with height until it melts away into the near emptiness around it. There is no single point you could touch and say, "Here, this is where the star ends." What we call the surface is only the layer where the gas finally becomes thin enough that light can slip free and travel across space to reach us. Below that layer, the star glows but cannot be seen through. Above it, the gas is clear. We see the glowing shell, and we call its width the size of the star. So already, the question is subtler than it sounded. When we ask how big a star is, we are asking how wide that glowing shell is, and for the largest stars, even that shell is uncertain, smeared across a soft and shifting zone rather than drawn as a sharp line. There is something else too, and it is the quiet heart of everything that follows. There are 3 different ways a star can be large, and they do not rise and fall together. A star can be large in mass, holding a great deal of matter. A star can be large in width, taking up a great deal of space. And a star can be large in brightness, pouring out a great deal of light each second. These 3 are not the same, and the most surprising fact in all of this is that the heaviest stars are not the widest stars, and the widest stars are not the heaviest. A star can hold 100 times the matter of our Sun, and still be far smaller across than a bloated, aging giant that holds only a handful of suns' worth of material spread impossibly thin. Mass is one kind of largeness. Width is another. And the answer to which star is the largest depends entirely on which kind of largeness we mean. Tonight we are climbing the ladder of width, the ladder of how much space a star fills, because that is the ladder that leads to the truly enormous, the stars so wide that the mind cannot quite hold them. We measure that width in different ways, depending on how near and how cooperative a star is. A few of the closest large stars are wide enough and near enough that their disks can be seen as the faintest smudges of light, and their width measured almost directly. For others, the light of several telescopes is woven together to sharpen a star from a single point into a measurable circle. When two stars orbit one another and pass in front of each other from our view, the careful timing of their dimming reveals the size of both with unusual precision. And for the most distant stars, size is inferred from color and brightness, because a star's color reveals its temperature, and a star that is cool yet blindingly luminous must be enormous to shine so brightly from so cool a surface. In nearly every one of these methods, the weakest link is distance. To know how large a star is, we must know how far away it lies, and the largest stars are far away, wrapped in dust, and difficult to pin down. This is why their measured sizes drift and change. It is not a flaw in the question. It is the nature of the answer. So let us begin gently at the bottom with something familiar and climb from there. It helps to sit a moment longer with the idea that a star has no real edge, because everything tonight depends on it. Think of how a fog gathers over a field at dawn. Near the ground it is thick and white, and you cannot see through it, and as it rises it thins, paling, until somewhere overhead it simply becomes the clear air again. There is no line where the fog stops. There is only a gradual fading. A star is like this, on a scale almost beyond imagining. Its glowing gas is dense and bright near the core, and it thins outward through layer after layer, until at last it fades into the thin gas between the stars. When we draw a circle and call it the size of the star, we are choosing a place in that fading where, by agreement, we say the star ends. For most stars, the fading is steep enough that the choice barely matters. For the largest, it matters a great deal, and that is one reason their sizes are so uncertain. Consider, too, how much of what we know about a star arrives carried only on light. We cannot visit these stars. We cannot lay a measuring tape across them. Everything we understand about their size, their temperature, their composition, their motion, comes to us written in the light they send across the dark. The color of that light tells us how hot the surface is, because hotter surfaces glow bluer and cooler surfaces glow redder, in a relationship as reliable as the glow of a heated iron shifting from dull red to white as it warms. The brightness of that light, once we know the distance it has crossed, tells us how much surface there must be to produce it. And from color and brightness together, patiently, the size of a star can be drawn out. Even for a star so far away, it is no more than a point. This is why distance matters so much, and why it troubles every measurement of the largest stars. A faint star could be a dim star nearby, or a brilliant star very far away, and only knowing the distance lets us tell which. For the nearest stars, distance can be measured directly by watching how a star appears to shift its position by a tiny amount as our world travels around the sun across the year, the same way a finger held up at arm's length shifts against the far wall when you look first with one eye and then the other. But the largest stars lie far beyond the reach of that simple method, out where the shifts grow too small to read cleanly, and so their distances and their sizes carry an unavoidable haze of uncertainty. We will return to this haze again and again as we climb, because it is woven into the very fabric of the question. It is worth admitting, gently, how strange it is that we can know any of this at all. No one has ever stood near another star. No instrument has ever touched one. Everything we understand about the sizes of stars, from the smallest ember to the largest hypergiant, has been read from light alone. Light that left those stars long ago and crossed unimaginable distances to arrive, faint and patient, at our instruments. And yet from that thin thread of arriving light, we have learned to measure the widths of suns. It is one of the quiet triumphs of looking carefully at the sky, that so much can be drawn from so little. The largest stars in the universe are known to us only as patterns in old light, and still we can say, with care, roughly how vast they are. There is a humility built into this that suits the night. Because everything depends on light and distance, every size we name carries a soft uncertainty, a gentle range, rather than a hard number. We do not say a star is exactly so wide. We say it is roughly so wide, probably within this range, depending on how far away it truly lies. And rather than being a frustration, this softness is honest and even restful. The cosmos is not a thing to be pinned down to a single decimal. It is a thing to be approached carefully, with our best looking, and left a little open. As we climb tonight, every number will carry this quiet openness, and that is exactly as it should be. The sun, our measuring stick, every step we take up the ladder tonight will be measured against a single star, and that star is our own. The sun is the unit. It is the ruler we will carry with us, and so it is worth holding it steady in the mind before we begin to climb, because everything that follows is a multiple of it. The sun is about 1,400,000 kilometers across. That is a little under 900,000 miles. It is a number large enough to lose your footing on, so here is a gentler way to feel it. About 109 Earths could be set side by side across the face of the sun, a long line of worlds laid edge to edge from one rim to the other. And by volume, more than 1 million Earths could be poured inside it and still leave room to spare. By any human measure, the sun is colossal. And yet, on the ladder we are about to climb, the sun is ordinary. It is a modest, middle-sized, yellow star, the kind that fills the galaxy in their billions. It is not large for a star. It is the baseline. When we say a star is 800 times the size of the sun, we mean 800 suns could be set across its width, and we are still nowhere near the top. Light leaves the surface of the sun and crosses the long emptiness to reach us in a little over 8 minutes. Every beam of sunlight that warms a face on a clear afternoon left its surface 8 minutes before. To circle the sun once, a passenger jet flying without rest would need roughly 6 months of continuous flight. Hold that image, because it will return when we reach the largest stars, and it will have changed almost beyond recognition. The sun shines the way most stars shine for most of their lives. Deep in its core, under crushing pressure and tremendous heat, hydrogen is fused into helium, and that slow fusion releases the light and warmth that fills the solar system. The sun has been doing this for billions of years, and it will continue for billions more. This long, steady middle age is the calm against which we measure the giants, because the giants are stars that have left this stable phase behind, or were born so massive that they could never have been calm at all. So the sun is our anchor. A yellow star, 1 million Earths in volume, 8 light minutes of sunlight, 6 months of flight to circle once. Keep it close. We are going to begin below it, among the small and the dim, because the height of a climb is only felt once you have stood at the bottom and looked up. There is more worth knowing about our measuring stick before we leave it behind, because the sun is not only a yardstick but a guide to how all stars work. It is a sphere of gas so hot that the atoms within it have been stripped of their outer parts, a churning, glowing plasma rather than anything solid. At its heart, the pressure and heat are so extreme that the cores of hydrogen atoms are pressed together and fused into helium, and in that fusion, a tiny fraction of their matter is released as energy. That energy then begins an unimaginably slow journey outward, bouncing and scattering through the dense layers above the core, taking many thousands of years to climb from the center to the surface, before finally escaping as the sunlight that crosses to us in 8 minutes. The sun's surface, which looks so smooth and steady from a distance, is in truth a restless sea. It is covered in countless churning cells, each one a column of hot gas rising, spilling its heat, cooling, and sinking back down, the whole surface simmering like the top of a slowly boiling pot. Each of these cells is roughly the size of a large country, and there are millions of them at any moment. Remember this image, because when we reach the largest stars, we will find the same churning, but on a scale so vast that a single such cell could be larger than the orbit of a planet. The physics is the same. Only the scale has changed, almost beyond recognition. And the sun, ordinary as it is among stars, is still the overwhelming ruler of its own small kingdom. It holds within itself the great majority of all the matter in the solar system. Every planet, every moon, every asteroid and comet, all of it together, is only a tiny remainder left over after the sun was made, scraps orbiting the central fire. When we say the sun is a modest, middle-sized star, we are speaking only of how it compares to other stars. Compared to everything near it, compared to every world that circles it, the sun is everything, the source of nearly all the light and warmth and matter in its realm. It is worth holding both of these truths at once. Vast beyond our scale, and yet only a baseline against the giants. That doubleness is the shape of the whole night. Hold the sun a moment longer, because there is a comfort in its steadiness that the rest of the night will lack. The giants we are about to meet are stars in transformation, swelling, shedding, pulsing, ending. The sun, by contrast, is calm. It has been burning steadily for billions of years, and it will burn steadily for billions more, neither growing nor shrinking in any way. A watching eye could notice across a human life or 1,000 human lives. It is the most reliable thing in our sky, rising and setting, warming the world, holding its size and its light with a constancy that feels almost like a promise. When we measure the giants against it, we are measuring the restless and the dying against the steady and the calm. And there is a scale comfort in remembering that, ordinary as the sun is among stars, it is more than enough for us. It is the source of nearly all the light and warmth and life in its realm. We will spend the night marveling at stars 1,000 times its width, and rightly so, but none of those distant giants warms a single face on a single morning. Our small, steady, middle-sized sun does that, every day, without fail. The largest stars are wonders to climb toward. The sun is the one that holds us. It is worth keeping that affection close as we leave it behind for the heights. The small stars at the bottom of the ladder, we begin our climb below the sun, among the small and the faint, because the scale of what waits at the top only becomes moving once we have felt how low the ladder reaches. It is tempting to imagine that most stars are like the sun, or larger. They are not. Most of the stars in the universe are smaller than the sun, dimmer than the sun, and far more patient than the sun. The galaxy is built, more than anything, from small stars. The most common stars in the universe are the red dwarfs. They are small, cool, and dim, holding far less matter than the sun, and they make up roughly 3 out of every 4 stars in our galaxy. For every sun, there are several of these quiet little embers, glowing faint and red and steady in the dark. They are the true majority, the ordinary citizens of the cosmos, and they almost never draw the eye. A typical red dwarf might be only a tenth to about half the width of the Sun. The smallest of them are not much larger across than the planet that rules the outer solar system, the Great Banded Giant, though a red dwarf holds far more matter squeezed into that small space. They are small and they are frugal. A red dwarf burns its fuel so slowly and so carefully that it can shine steadily for trillions of years, far longer than the present age of the universe. Not a single red dwarf has ever died of old age, anywhere, because the universe itself is not yet old enough for even one of them to have run out. They are, in their quiet way, nearly immortal. The nearest star to our own Sun is one of these red dwarfs. Even though it is the closest star in all the sky, it is so small and so dim that it cannot be seen with the unaided eye at all. You could stand under the darkest sky on the clearest night and never find it without a telescope. At this end of the ladder, smallness and faintness travel together. The smallest stars are also the hardest to see. Below the red dwarfs lies a soft boundary, a line that separates the stars from the not-quite stars. An object with too little matter can never light the sustained fusion fire in its core that makes a true star. These are the brown dwarfs, sometimes called failed stars, glowing only dimly from the leftover heat of their formation and slowly cooling over the ages. In width, they are close to a large planet, near the size of the Great Banded Giant of our own solar system, and here a strange rule appears for the first time. Adding more matter to one of these objects barely changes its width, because gravity simply squeezes the new material tighter. Mass goes up, but size hardly moves. It is our first hint that mass and width are different things, and that the relationship between them is anything but simple. So the bottom of the ladder is a place of small, dim, patient things. Red dwarfs by the billions, glowing faint and red, and lasting nearly forever. Brown dwarfs below them, barely glowing at all. And against all of these, even our ordinary yellow sun is already a step up. From here, the climb begins to rise. Spend a little longer among the small stars, because there is a gentle wonder in them that the giants can make us forget. The red dwarfs are not failures or lesser things. They are the most successful stars in the universe, the most numerous, and by far the most enduring. While the great bright stars flare and die in a few million years, a red dwarf settles in for the very long haul, fusing its hydrogen so slowly and so thoroughly that it can keep its small, steady flame burning for many trillions of years. Long after the last bright stars have died, long after star formation across the cosmos has all but ceased, the red dwarfs will still be glowing, faint and red and patient, the final lamps left lit in a darkening universe. They are thorough in a way larger stars are not. A massive star fuses only the hydrogen in its central core before its life turns toward its end, leaving much of its fuel untouched in its outer layers. But a red dwarf stirs itself slowly throughout, mixing its material, drawing nearly all of its hydrogen down into the fusing center over the ages, wasting almost nothing. It is the most frugal kind of star there is, and frugality in the cosmos is the secret of long life. The small, dim, easily overlooked red dwarf will outlast every brilliant giant by a margin so vast that the giants' entire lives are a single bright instant by comparison. The smallest true stars sit just above the line where fusion can begin at all, holding only a fraction of the sun's matter, glowing a deep, dim red. Below that line lie the brown dwarfs, the objects that never quite became stars, and they fade slowly over the ages from a faint, warm glow toward darkness. And it is worth noticing the strange rule that governs their size, because it foreshadows something important. For these small, dense objects, adding more matter does not make them larger, It makes them smaller because the extra weight pulls the whole body into a tighter, denser ball. Up to a point, the more matter you pour in, the more gravity compresses what is already there. Only when fusion ignites and pushes back outward does the relationship reverse. Mass and size, even here at the bottom, refuse to march together in a simple line. That refusal is the quiet theme of the whole climb, and we have heard it now from the very lowest rung. There is one more thing to notice at the bottom of the ladder, a thought to carry upward with us. The small stars are not only the most numerous and the most enduring, they are also, in their way, the future of the cosmos. As the ages pass and the great bright stars burn out one by one, the universe will grow slowly redder and dimmer, until at last the small patient red dwarfs are nearly all that remain, glowing faint and steady in a quieting sky. The stars we overlook tonight, the dim ones at the bottom of the ladder, will be the last lamps still lit when the giants are long gone. There is a gentle justice in that, the smallest and humblest outlasting the grandest by spans of time almost beyond counting. And it reframes the whole climb. We are about to ascend toward the largest, brightest, most spectacular stars in the universe, and they are magnificent. But they are also rare, and brief, and few. For every one of them there are countless small red embers, quietly outliving them, asking nothing, drawing no eye. The summit we are climbing toward is real and worth reaching. But the bottom of the ladder, where we stand now, is where most of the stars actually live, and where the light will linger longest. It is worth holding both in mind as we rise, the rarity and brilliance of the top, the patience and abundance of the bottom. It is worth dwelling too on how the smallness of these stars shapes the worlds that might circle them. A red dwarf is so dim and so cool that any world warm enough to hold liquid water would have to orbit very close in, far closer than our own world orbits the sun, huddled near the small red fire for warmth. And a world that close would likely turn one face always toward its star, the way the moon turns one face always toward the earth, so that one side knew endless red day and the other endless night. The skies of such worlds would be lit by a great, dim red sun, unmoving on the horizon, casting a perpetual deep crimson light across a landscape caught between fire and dark. There is a strange tenderness in imagining these places, lit so softly, warmed so gently, beneath stars that will outlast every brilliant giant in the sky. The small stars are not only the most numerous and the most enduring, they may also be, in the long run, the most common homes for whatever worlds the cosmos holds, quiet red hearths around which planets gather close for warmth. As we climb away from them toward the great bright giants, it is worth carrying the thought that the future of the cosmos, and perhaps much of its quiet life, belongs not to the giants, but to these small, patient red lamps at the bottom of the ladder. The dense, little ghosts. Not every small star is small because it was born that way. Some of the smallest, densest objects in the universe were once far larger, and they were crushed down into almost nothing at the end of their lives. They belong here, on the ladder, near the bottom, as a quiet counterpoint to everything we are about to climb toward. They are the same matter as the giants, folded into almost no space at all. When a star, much like the sun, reaches the end of its life, it does not vanish. It sheds its outer layers gently into space and leaves behind its bare, exposed core. This remnant is a white dwarf, and it is a strange and dense thing. A white dwarf packs roughly the entire mass of the sun into a sphere about the size of the Earth. Imagine that. A star's worth of matter compressed until it is no wider than our small rocky world. A single spoonful of white dwarf matter would weigh as much as a heavy truck. It no longer burns. It simply glows with leftover heat, cooling so slowly that it will take longer than the present age of the universe to fade away completely. There is a denser remnant still, left behind by stars more massive than the Sun. When such a star dies, its core can be crushed far beyond the white dwarf stage, squeezed until the matter itself is rewritten into a sphere only about 20 kilometers across that holds more mass than the entire Sun. This is a neutron star, a star the size of a city. A single sugar cube of its matter would weigh about as much as a mountain. It is one of the densest objects that exists anywhere, and it began as something enormous. These ghosts make a point that will matter greatly when we reach the top of the ladder, and they make it from the opposite direction. Here is enormous mass folded into almost no space at all. A whole sun inside the Earth. More than a sun inside a city. The giants we are climbing toward are the perfect mirror of this. They are modest amounts of mass spread across an unimaginable volume. The white dwarf and the neutron star are heavy and tiny. The hypergiant at the summit is light for its size and vast. Mass and width are not the same thing. We will see that truth from both ends before the night is done. It is worth pausing on the strangeness of it. The widest stars in the universe, the ones we are climbing toward, will at the end of their lives collapse into objects like these, into neutron stars or into black holes, into some of the smallest and densest things that exist. The ladder, in a sense, folds back on itself. The largest become the smallest. The most spread out become the most compressed. But that is the summit and the ending, and we have a long, gentle way still to climb. Let us return to the steady middle, where the sun lives, and start upward in earnest. Linger with the dense little ghosts a while longer, because they are among the strangest and most peaceful objects in all of nature, and they have a great deal to teach about the meaning of size. A white dwarf no longer fuses anything. It has no fire left to burn. It shines only with the stored heat of its long life, radiating it away into space, across spans of time so vast that not a single white dwarf anywhere has yet had time to cool completely to darkness. They are the slowly fading embers of dead stars, glowing faintly white at first, then yellow, then red, over ages longer than the present age of the universe. To look at a white dwarf is to look at a sun's worth of matter, quietly cooling inside a body no larger than a world. What holds a white dwarf up, now that its fire has gone out, is not heat at all, but a stranger and deeper kind of resistance, a property of crowded matter itself, a refusal of its tiniest parts to be pressed together past a certain point. This same quiet stubbornness holds the star against its own gravity forever, so long as the star is not too heavy. But if too much matter is gathered, even that resistance fails, and the collapse goes further, into the neutron star, where the crushing is so complete that the matter is rewritten into something almost entirely new. A single, vast core of densely packed particles, a sun's worth of mass folded into a sphere you could drive across in an hour. And there is something profound in setting these ghosts beside the giants we are climbing toward. The neutron star and the great red hypergiant might both have begun their lives with a similar amount of matter, a few dozen times the mass of the sun. One has spread that matter across a volume so vast that the inner planets could be lost inside it. The other has crushed nearly the same matter into a ball the size of a city. The same amount of stuff, the same starting material, taken to the two opposite ends of what is possible. Diffuse beyond belief, or dense beyond belief. The cosmos contains both extremes, and a single star, across its life, can travel from one to the other, swelling to enormous size in its old age, and then collapsing, at the very end, into one of these tiny, dense, silent ghosts. The largest and the smallest are not opposites in the cosmos. They are stages of the same long story. There is a final thought to carry up from the dense little ghosts, and it is perhaps the gentlest of all. These collapsed remnants, the white dwarfs and the neutron stars, are not endings in the bleak sense. They are quiet states of rest. A white dwarf has finished its long life of burning and now simply cools, slowly and peacefully, across spans of time longer than the present age of the universe, asking nothing, doing nothing but fading by the faintest degree. There is no struggle left in it, no further change to fear. It is a star at rest, holding the memory of its life inside a small, dense body, cooling toward a long quiet. And these ghosts close a circle that we will see completed at the very top of the ladder. The largest stars, the vast red hypergiants we are climbing toward, will end their lives by collapsing into objects like these, into neutron stars, or into black holes. The widest things in the universe fold down, at the last, into some of the smallest and densest. So the bottom of the ladder and the top are secretly joined. The dense little ghosts at our feet are what the giants at the summit will one day become. We are not climbing away from these small remnants. We are climbing toward the stars that will, in time, become them. The ladder is a circle, and we have already seen its far end. The steady middle, for most of its long life, a star does the same quiet thing. It fuses hydrogen into helium in its core, in steady balance, neither growing nor shrinking by much, simply shining. Astronomers call this long, stable stretch the main sequence, and it is where stars spend the overwhelming majority of their existence. The Sun is in the middle of its own main sequence life right now, and it has been there for billions of years. Where a star sits along this main sequence is set almost entirely by one thing: the amount of matter it was born with. Mass is destiny here. A star born with much more matter than the Sun is larger, hotter, bluer, and far more luminous. A star born with less is smaller, cooler, redder, and dimmer. The whole sequence is a single long slope, from the small, cool red stars at one end to the large, hot blue stars at the other, and a star's birth mass decides where on that slope it will sit for almost all of its life. But there is a price for being large and bright on the main sequence, and it is a steep one. The most massive, most luminous stars burn through their fuel at a furious rate, and so they live only a few million years before exhausting it. They are brilliant and brief, like a fire built too high. The small, cool red stars at the other end sip their fuel so slowly that they last for trillions of years. The brighter the star, the shorter its life. Largeness and brevity are bound tightly together, and we will meet that binding again at the very top of the ladder. A star like the Sun sits comfortably in the middle of this slope. A few billion years of its life already spent, a few billion more still ahead. Across this long, stable stretch, its width barely changes at all. It is neither growing nor shrinking in any way a watching eye would notice. It is simply holding steady, burning calmly, the way most stars do for most of their lives. The largest stars on the main sequence, the hot blue massive ones, may be several times the Sun's width, even up to a dozen times or so. That is genuinely large. And yet, on the ladder we are climbing tonight, it is still only the foothills. The truly enormous stars, the ones that fill the imagination, are not on the main sequence at all. They have left it behind. And here we arrive at one of the most beautiful and quietly surprising facts in the whole story. To become truly vast, a star must first begin to die. The swelling that makes a star enormous is not a sign of its prime. It is a symptom of its aging. The giants are stars in their final chapters. Let us climb up into them now, gently, and see how a steady middle-aged star becomes something colossal. There is more to say about the steady middle, because it is where the rules that govern the whole ladder are written. The main sequence is not a list of separate kinds of star so much as a single continuous slope, and every star's place on it is set, almost entirely, by the one thing it cannot change: the amount of matter it was born holding. A star cannot choose to be hotter or brighter than its mass allows. The weight of its own gas determines the pressure and temperature at its core, and those in turn determine how fiercely it fuses, how hot its surface burns, what color it glows, and how long it will live. Mass is the single dial, and everything else follows from it. This is why the slope runs so cleanly from one end to the other. At the dim, cool red end sit the small stars, holding little matter, fusing gently, lasting almost forever. At the brilliant, hot blue end sit the massive stars, holding a great deal of matter, fusing furiously, burning out fast. The sun sits in the comfortable middle, neither frugal nor reckless. And the cruel arithmetic of it is that the more matter a star holds, the more of it there is to burn, but the faster it must burn it, and the faster wins. A star with 10 times the sun's matter does not live 10 times as long. It lives a tiny fraction as long, because its fire roars so much more fiercely. Brilliance is bought with brevity, every time. And it is worth saying plainly, before we climb into the giants, that a star on the main sequence is not yet large in the way we are chasing tonight. Even the most massive blue stars, blazing with the light of many thousands of suns, are only a handful of times the sun's width while they remain on the main sequence. They are heavy and hot and bright, but not yet vast. The vastness, the true enormity of width, comes only later, only after a star has spent the hydrogen in its core and begun the long transformation of its old age. To climb the ladder of size, we have to follow stars off the main sequence and into their final chapters. The largest stars in the universe are, every one of them, stars that have begun to die. There is a strange tenderness in that, and we carry it with us as we climb into the giants now. One more image will help before we leave the steady middle and begin to climb in earnest. Imagine all the stars in the universe gathered and sorted by size, laid out along a single long slope, from the smallest to the largest. The overwhelming majority would cluster down at the small end, the red dwarfs and the modest stars, a great crowded multitude of small steady lamps. The sun would sit a little above the middle of that crowd, comfortably ordinary. And then the slope would thin out rapidly toward the large end, the giants growing rarer and rarer, the supergiants rarer still, until at the very top stood only a tiny scattered handful of the largest stars, far apart, each one alone against the sky. Size, among stars, grows rarer the greater it becomes. This is the shape of the journey we are on. We begin in the crowded multitude at the bottom, among the countless small stars, and we climb toward the lonely few at the top, where the giants stand scattered and rare. Each step up the ladder takes us toward fewer and fewer stars, larger and larger, more and more extraordinary. By the time we reach the summit, we will be among objects so rare that only a handful are known in the entire galaxy. The climb is not only upward in size, it is inward toward rarity, toward the small company of the greatest stars, the ones the cosmos makes only seldom and keeps only briefly. The first great swelling. This is the turning point of the climb, the place where stars begin to grow truly large. And it begins, strangely, with running out of fuel. To understand the giants, we have to understand why a dying star swells rather than simply fading. And the reason is a quiet and elegant piece of physics that turns an ending into an expansion. Through all its long main sequence life, a star fuses hydrogen into helium in its core, and the heat of that fusion pushes outward, balancing the inward pull of gravity. But the core's supply of hydrogen is not endless. Eventually it runs low, and the fusion in the very center falters. With less heat pushing out, gravity gains the upper hand, and the core begins to contract. As it contracts, it grows hotter, far hotter than before. That rising heat does something remarkable. It ignites fusion not in the core itself, but in a shell of hydrogen surrounding the core, a burning layer wrapped around the shrinking center. And this shell, heated by the contracting core beneath it, burns far more fiercely than the core ever did. Now the star is releasing more energy than before, not less. The dying has made it brighter. All that new energy has to go somewhere, and it pushes outward against the star's outer layers, lifting them, expanding them, swelling the whole star outward. As the outer layers spread across a far greater volume, they cool, and as they cool, they redden. And so the star balloons. A hotter core drives a cooler, vastly larger surface. The star that was once a modest yellow point becomes a swollen, glowing, deep red giant. This is how smallness becomes enormity. Not through growth in the living sense, but through the slow, luminous unraveling of a star's final age. The scale of this swelling is hard to overstate. A star, much like the sun, in becoming a red giant, can expand to tens of times its original width, and then, in the later stages, to over 100 times. The same star, the same amount of matter, simply spread across an enormous new volume, thin and cool and red and immense. Nothing has been added. The star has only opened outward, like something unfolding in slow motion across thousands of years. And here is the gentle truth folded inside this physics. Every red giant we pass as we climb is a glimpse of a future. It is what happens to ordinary stars when their steady middle age finally ends. The swelling is not violence. It is age. It is the long, slow, luminous exhale of a star that has spent its core and begun the final transformation. We are about to walk among these swollen stars now, the giants overhead, and one of them, in the deep future, will be our own. It is worth tracing the swelling more slowly, because it is one of the most beautiful processes in nature, and understanding it changes how the giants feel. When the core of an aging star first runs low on hydrogen, nothing dramatic happens at once. The change is quiet and internal. The core, no longer fully supported by its own fusion, begins to settle and contract under its own weight, and as any gas does when it is compressed, it grows hotter. That rising heat reaches the unburned hydrogen in a thin shell wrapped around the core, and that shell, now hot enough, ignites. The star has moved its fire from its center to a layer surrounding the center, and that shell burns hotter and faster than the old core fire ever did. Now the star is caught in a strange and lovely imbalance. Its center is contracting and heating, while its surface, fed by the new energy from the shell, is pushed outward and expands. The star grows from the outside, even as it shrinks at its heart. The outer layers, lifted across an ever greater volume, spread thin and cool, and as they cool, they shift in color from white or yellow toward orange and deep red. A modest star can swell over this stage of its life to tens of times its former width, and the most extreme can pass 100 times. The matter has not increased. The star has simply opened, like a slow bloom, across thousands of years. There is something to notice in the timing, too, a gentleness that suits the night. This swelling does not happen in an instant. It unfolds across spans of time so long that, to any watcher, the star would seem perfectly still, a fixed red lamp in the sky, even as it expands. The transformation is real but unhurried, a process measured in the slow turning of stellar ages rather than in anything a single lifetime could witness. And every star massive enough will pass through some version of it, swelling in its old age before its final end. The night sky is full of stars at every stage of this journey, some just beginning to swell, some fully bloomed into giants, some already shedding their outer layers into the dark. We're about to walk among the bloomed ones now, the giants overhead, and to remember that one of them, in the long future, will be our own sun. It is worth pausing on a quiet paradox folded into all of this, because it is one of the loveliest things in the life of a star. The swelling that makes a star a giant is driven by the contraction of its core. The outside grows because the inside shrinks. As the spent core settles and compresses and heats, it drives the fierce shell burning that lifts the outer layers and inflates the star to enormous size. So the giant is, at its very heart, a star pulling inward, even as its surface reaches outward across an ever greater volume. The largest, most swollen stars are large precisely because something deep inside them has begun to collapse. Expansion and contraction happening at once in the same star at different depths. There is a strange harmony in it, an unfolding and an infolding bound together. This is also why the swelling is a one-way road. A star does not become a giant and then return to being a modest main sequence star. The contraction of the core is the slow march toward the end, the settling of the spent center that fusion can no longer fully hold up. Once a star begins to swell, it has entered the final chapters of its life, and it will move forward through them, fusing heavier elements, swelling further or shedding its layers, until at last it reaches whatever ending its mass has always destined for it. The giants overhead, then, are not stars in their prime grown large. They are stars in their old age, opened wide and glowing red, walking forward, slowly and without struggle, toward their endings. The size is the sign of the journey's lateness. The giants overhead and the fate of the sun. If you look up on a clear night, some of the brightest warm-colored stars you can see are giants, stars that have already left the steady middle of their lives and swollen into something far larger than the sun. They glow with the warm orange and red light of cooling surfaces, the unmistakable color of a star in its later age. They are the first rung of the ladder, where the word giant becomes literally, physically true. Some of these are orange giants, only modestly larger than the sun, stars that have just begun to swell and have not yet reached their full expansion. Others are well-developed red giants, tens of times the sun's width, their surfaces cooled to a deep, warm glow as their outer layers spread thin across an enormous volume. A giant perhaps 30 or 40 times the width of the sun would, if set in the sun's place, swallow the orbit of the innermost planet entirely and loom vast and orange in the sky of any world that remained. These are not rare or exotic objects. They are scattered across the night sky, visible to the unaided eye, the nearest examples of what aging does to a star. To stand on a world orbiting such a giant would be to live beneath an enormous, dim, warm sun, far larger across the sky than our own, glowing a deep and gentle red. It would not blaze the way our sun blazes. Its light would be softer, redder, spread across a far greater face. There is something almost restful in the image, a star grown huge and slow and warm in its old age. And this is the future of our own sun. In the far distant future, billions of years from now, the sun will exhaust the hydrogen in its core, and it will begin the same swelling we have just traced. It will become a red giant. It will expand outward, perhaps to over 100 times its present width, swallowing the innermost worlds of the solar system as it grows, glowing enormous and red where once it was a small yellow point. Any creature standing on a distant surviving world would see it fill a great portion of the sky, a vast warm presence where the familiar sun had been. Then, gently, it will let go. A star like the sun does not end in violence. After its time as a red giant, it will shed its swollen outer layers softly into space, casting them off in slow, glowing shells that drift outward and fade. What remains will be the bare core, settling down into one of the dense little ghosts we met near the bottom of the ladder, a slowly cooling white dwarf, no larger than the Earth, holding the memory of a star inside a body the size of a world. So every red giant overhead is a kind of mirror held up to our own star's distant old age. The swelling, the reddening, the enormous gentle glow, and then the soft letting go. We are climbing past the future of the sun, and we are not nearly at the top. Above the ordinary giants wait stars larger still, and the climb grows steeper from here. There is a deeper comfort to draw from the giants overhead and from the sun's place among their future ranks if we sit with it gently. We tend to think of a star's swelling into a red giant as a kind of catastrophe, an ending. But seen across the long view, it is simply a phase, as natural as autumn, as the reddening of leaves before they fall. The star is not failing. It is changing, passing through the late chapter that its mass has always destined it for, doing exactly what stars of its kind have always done. There is no struggle in it, no resistance, only the slow unfolding of what was always going to come. Picture again a world orbiting one of these aging giants, far in the future or far across the galaxy. Its sky would hold an enormous, dim, gentle sun, glowing deep red and far larger across than our own, casting a soft, warm light over the land. The fierce white glare we know would be gone, replaced by something slower and redder and easier on the eye. Such a star floods less harsh energy onto its worlds, even as it grows huge, because its surface, spread so thin, has cooled. There is a strange peacefulness in imagining it, a landscape lit by a vast, calm crimson sun that fills a quarter of the sky and yet does not blaze. For our own sun, this future lies billions of years away, almost unimaginably distant in time. When it comes, the sun will swell and redden and grow enormous, reaching out to engulf its innermost worlds, looming vast over whatever remains. And then, having no great mass to drive it further, it will not explode. It will simply, gently, let go. Its swollen outer layers will drift away into space as slow, glowing shells, beautiful and expanding, and at the center the bare, exhausted core will be left behind, settling into a small, dense, white ember no larger than the Earth. The sun's whole long story will end not with violence, but with a quiet exhalation and a slow cooling into the dark. Every red giant we can see tonight is rehearsing that future for us, showing us, in advance and at a safe distance, the shape of our own star's gentle old age. We climb on now, past the ordinary giants, towards stars that will not end so quietly. There is a gentleness worth gathering from this rung before we climb higher, a way of seeing the giants overhead not as warnings, but as company. Every one of them is a star doing exactly what its nature asks, passing through the late chapter that its mass laid out for it long ago, without struggle and without haste. They swelled because they aged, and they aged because they had burned long and well. And the swelling is simply what comes after a long life of burning. To see a red giant is to see a star at peace with its own lateness, opened wide and glowing warm, neither clinging to its youth nor hurrying toward its end. And it is worth remembering how slow all of this is, how far beyond any rush. The swelling of a star into a giant unfolds across spans of time so vast that 1,000 human lifetimes would not see it change. To any watcher, the giant simply hangs in the sky, a steady, warm red point, as fixed as anything. The transformation is real, but it moves at the pace of the cosmos, which is to say it moves so gently that, on any scale we know, it does not seem to move at all. There is rest in that, in knowing that even the great changes of the stars are unhurried beyond imagining, and that the giant overhead will glow warm and red and seemingly unchanging for longer than we can hold in mind. We climb on now, past these peaceful aging giants, toward the supergiants and the summit, carrying their calm with us. Bright giants and blue giants. Above the ordinary giants, the ladder continues upward into the bright giants and the blue and blue-white giants, stars that are more massive, more luminous, and in many cases, hotter than the red giants we have just passed. These are stars that were either born large and hot or have swollen from massive beginnings, and they carry us toward the supergiants that wait higher still. Here we meet again the quiet truth that brightness and width are not the same. Some blue giants are not enormously wide at all. They may be only a handful of times the sun's width, and yet they blaze with the light of thousands of suns, pouring out their energy from a relatively compact, ferociously hot, blue-white surface. A star can be modest in size and staggering in brightness if its surface is hot enough. The hotter a surface burns, the more light each patch of it throws out, and so a small but blazing star can outshine a far larger but cooler one. Certain of the brilliant blue-white stars in the winter sky are exactly this kind of object, bright giants and supergiants whose light has crossed centuries of empty space to reach us. Each is many times the width of the sun and tens of thousands of times as luminous, and the light arriving tonight left those stars long ago, traveling the whole intervening distance at the speed of light, just to be seen. When you look at one of those brilliant blue points, you are seeing a furnace of almost unimaginable output, made to look like a quiet jewel only by the vastness of the distance between. These hotter, more massive stars live differently from the sun, and they end differently too. They are massive enough that they will not fade away gently into white dwarfs the way the sun will. Their greater mass drives them onward, into the supergiant stage and beyond, toward far more dramatic endings. They are bound for the next great step up the ladder, the supergiants, where width becomes truly staggering and where the numbers begin to strain the imagination in earnest. So we pause here, only briefly, on this middle high rung. Bright and blue and hot, luminous out of all proportion to their size, the blue giants are a reminder that the cosmos keeps more than one kind of record. Some stars are champions of brightness. Others, the ones we are climbing toward, are champions of sheer size. They are not always the same stars. And it is the champions of size we are chasing tonight. Upward, then, into the supergiants. The blue giants and bright giants deserve a longer look because they sharpen the central puzzle of the whole night, the difference between being bright and being big. A blue giant burns with a surface far hotter than the sun's, and heat, in a star, is enormously generous with light. Double the temperature of a surface, and it pours out not twice but many times as much light from every patch. So a blue star, even one not especially wide, can blaze with a brilliance that dwarfs far larger but cooler stars. Its fierceness comes from its heat, not its size. It is a small window opened onto a furnace, rather than a vast surface glowing gently. This is why the brightest-looking stars in the sky are not always the largest, and the largest are not always the brightest. A cool red giant, vast across, glows only dimly from each patch of its enormous surface, and so its great size yields a softer light than its width alone might suggest. A hot blue star, compact by comparison, throws out a fierce light from a far smaller body. Brightness and size pull in different directions, governed by the two separate dials of temperature and surface area, and only when we hold both in mind can we read a star correctly. It is the same lesson the whole ladder keeps teaching, arriving now in the language of light. These hot, massive stars also live under a kind of sentence that the gentle red giants do not share. Their great mass, which makes them so bright, also drives them onward through the stages of their lives at tremendous speed and toward far more violent ends. They will not fade quietly into white embers. They are bound to swell into supergiants, to fuse their way through heavier and heavier elements, and at last to end in the great collapse and brilliant scattering that awaits the most massive stars. The blue giant is a star, living fast and headed somewhere dramatic. And on its way, if it is massive enough, it will pass through the supergiant stage, swelling to a size that begins, at last, to approach the summit we are climbing toward. So we leave the blue giants behind, carrying their lesson about light, and step up into the supergiants, where width itself becomes staggering. There is a quiet lesson in the blue giants worth carrying to the summit about how easily the eye is fooled. When we look up at the night sky, the stars that catch our attention, the brightest points, are not the nearest stars or the largest stars. They are most often distant, luminous giants and supergiants, blazing so fiercely that even across vast distances they outshine the small nearby stars. The humble red dwarf next door is invisible, while the brilliant blue giant far across the galaxy burns bright enough to name. The sky we see is a sky of the luminous few, not the numerous near. Our eyes are drawn to brightness, and brightness is not nearness, and brightness is not size. So the night sky itself is a kind of gentle deception, a scattering of the brightest beacons across an unseen multitude of dimmer, closer, smaller stars. When we admire the brilliant points of a constellation, we are admiring distant furnaces, while the quiet majority of stars, the small red lamps that fill the galaxy, go entirely unseen. It is worth remembering this as we climb toward the largest and brightest stars. They are magnificent, and they are real, but they are also the rare and shining exceptions, lifted into our notice by their fierce light, while the true population of the cosmos burns small and dim and patient below the threshold of the eye. The supergiants. Now the scale begins, in earnest, to strain the imagination. The supergiants are the swollen, late-life forms of stars born with many times the mass of the sun, and they are the second largest things on the whole ladder, standing just below the summit. To climb into them is to leave behind every familiar comparison and begin dealing in numbers that the mind can state but cannot quite picture. A supergiant is what a high-mass star becomes after it leaves the main sequence. Born with far more matter than the sun, Such a star fuses its way through heavier and heavier elements in a series of nested shells, and as it does, it swells enormously. The red supergiants are the largest by width, cool and deep red and bloated to hundreds of times the width of the Sun. The blue supergiants are hotter and somewhat more compact, but still vast and tremendously luminous, among the brightest individual stars in any galaxy. The luminosity of these stars is difficult to hold in the mind. A single supergiant can outshine the Sun tens of thousands, even hundreds of thousands of times. If one were placed where the Sun is, it would flood the solar system with so much light and heat that nothing could remain as it is. And yet, for all that fury, these stars are doomed to be brief. Such luminosity burns through fuel at a furious pace, and so the supergiants live only a few million years, a mere flicker against the trillions of years a red dwarf will quietly endure. To be this large and this bright is to be short-lived. The ladder's highest rungs are also its most fleeting. Look up into the right constellations, and you can find red supergiants with the unaided eye. One of the most famous marks, the shoulder of a well-known winter figure, a deep orange-red star roughly 700 to 900 times the width of the Sun. Set it in the Sun's place, and its surface would reach out past the orbits of the inner planets, swallowing them entirely, possibly reaching out toward the orbit of the great banded giant. A single star, where an entire inner solar system now lies. That is the scale we have climbed to. This same star is also a perfect lesson in why the edge of a star is such a soft idea. Its surface boils and churns, with enormous rising and sinking cells of gas, and it is wrapped in clouds of dust that it has cast off into space. Its measured width changes depending on the wavelength of light used to look at it and the era in which it was measured. It is not a fixed sphere, but a breathing, shifting, uncertain thing. And asking for its exact width is like asking for the exact edge of a cloud. Another famous red supergiant forms the bright red heart of a summer constellation, several hundred times the width of the Sun, slowly shedding its outer layers into a vast surrounding nebula of its own making. And among the most luminous stars the unaided eye can see is a distant blue-white supergiant whose true output runs well over 100,000 suns, appearing to us as only a moderately bright star, purely because it lies so staggeringly far away. These are the supergiants, the second highest rung. Above them wait only the very largest stars in the universe, the summit toward which this whole climb has been rising. The supergiants reward a slower walk, because they are where the scale of the night first becomes genuinely hard to hold. A red supergiant of 700 or 800 times the Sun's width is already an object that defeats the imagination. Set such a star where the Sun is, and the innermost worlds of the solar system would lie deep inside it, their orbits buried within the star's thin red glow. A signal of light which crosses our own Sun in seconds would take the better part of an hour to cross the face of such a supergiant. We have left behind every scale that human experience can grasp, and we are still only on the second highest rung. And yet, for all their size, these stars are governed by the same gentle physics we have been tracing all along. The red supergiant is a high-mass star in its old age, swollen by the same shell-burning process that turns a modest star into an ordinary red giant, only carried to a far greater extreme because the star holds so much more mass to begin with. It fuses its way through element after element in nested shells around its core, building heavier ash as it goes, and with each stage it adjusts and swells. The supergiant is not a different kind of thing from the giant. It is the same process, the same swelling, the same reddening, run on a star massive enough to take it to an extraordinary scale. The luminosity of these stars is as staggering as their size. A red supergiant can outshine the sun 100,000 times or more, and a blue supergiant can blaze even more fiercely still. If one of the most luminous supergiants were set at the distance of the nearest stars, it would shine in our sky brighter than anything but the sun and moon, a fierce point of light, visible even in daylight. That such stars appear to us as ordinary points, or are invisible to the unaided eye entirely, is only a measure of how staggeringly far away they lie. Their light has crossed centuries, sometimes thousands of years, of empty space to reach us, dimming with the distance until a furnace becomes a faint star. And remember always the price of that brilliance. These stars live only a few million years. They are the briefest of all, burning so hard and so bright that their fuel is spent almost as soon as it is lit. The largest and most luminous stars are also the most fleeting, here and gone in a cosmic instant. There is a further wonder hidden in the supergiants, which is how much they give back to the cosmos. As these enormous stars fuse their way through heavier and heavier elements in their final ages, they become factories, building in their cores the very substances that rock and water and living things are made from. The carbon, the oxygen, the heavier elements that fill the worlds and the bodies of the cosmos, much of it is forged inside stars like these, in their late lives and in their endings. And because supergiants shed their outer layers so freely, in slow winds and great castings off, they return this newly made material to the space around them, seeding the clouds from which new stars and new worlds will one day form. So a supergiant is not only an ending, but a giving. It takes the simple hydrogen and helium it was born with, and works it, over its brief, furious life, into richer and heavier substance, and then it pours that substance back out into the dark. The atoms scattered by the supergiants drift for ages through space, mingling with the great clouds of gas and dust, until gravity gathers them once more and a new star ignites, with new worlds forming around it, built in part from the ashes of stars that died long before. The largest stars are links in this slow chain of making and returning, and every world, every rock, every living thing carries within it atoms forged in the hearts of stars now long gone. To look at a supergiant is to look at a stage in this endless, patient recycling of the cosmos. It is worth noticing how a supergiant differs from the ordinary giants we pass just below it, because the difference is one of degree carried to an extreme. An ordinary red giant is an aging star of modest mass, swollen tens of times beyond its former width. A red supergiant is an aging star of great mass, swollen hundreds of times, and in the most extreme cases, nearly 1,000. The same swelling, the same reddening, the same shell burning that lifts the outer layers, only carried far further because the star holds so much more matter and so much more energy to drive the expansion. The supergiant is the giant's larger, brighter, briefer cousin, the next great step taken by the most massive stars on their way toward the summit. And because they are so massive, supergiants do not end as the ordinary giants do. A modest red giant will gently shed its layers and settle into a small white ember. But a supergiant carries too much mass for so quiet a fate. It will fuse its way through heavier and heavier elements, building toward the end, until its core can hold itself up no longer, and then it will collapse and scatter its substance in the brilliant ending that awaits the most massive stars. The supergiant is a star living large and bright and brief, headed toward a dramatic close, and on its way, it grows vast enough to stand just below the very largest stars in the universe. We have one rung left to climb, and it is the highest of all. And as we take that last step upward, We carry with us everything the climb has taught, that size and brightness and mass are three separate things, that the largest stars are the cool and aging ones, and that the greatest stars are also, always, the rarest and the most fleeting. The boiling, shifting surfaces. Before we step onto the summit, it is worth lingering on what the surface of one of these enormous stars is actually like, because it explains so much about why their sizes are uncertain, and because it is a strangely peaceful thing to imagine. The largest supergiants and hypergiants do not have smooth, calm faces. They have surfaces that heave and churn and breathe. At supergiant sizes, the star's gravity at its surface becomes extraordinarily weak. The outer layers are so far from the dense core, spread so thinly across such an enormous volume, that they are held on only loosely. The star cannot quite keep a firm grip on its own outermost gas, and so it steadily sheds material into space, in a slow, dense, outflowing wind, losing the equivalent of whole worlds of matter over the ages. A supergiant is always, gently, leaking itself into the dark around it. The surface itself is not still. On the Sun, the churning cells of rising and sinking gas are small, numbering in the millions across its face. But on a vast red supergiant, the same kind of churning happens on a colossal scale. The surface is divided into only a handful of titanic convective cells, each one larger across than the orbit of a planet, rising and sinking, swelling and collapsing over months and years. The star flickers and dims and brightens as these enormous cells turn over. It does not hold a single brightness or a single size. It breathes. This is why the width of such a star is never truly one number. As the great cells rise and fall, as the loosely held outer gas swells and contracts, the star's measured size shifts. Measure it 1 year, and you find one value. Measure it again later, and you find another, and both are honest. The star has genuinely changed in the time between. We are not measuring a fixed marble. We are measuring something closer to a slow, glowing red tide, forever moving. There is something quietly comforting in this, once the strangeness settles. We tend to imagine the largest stars as fixed, hard, definite things, monuments standing in the dark. But they are soft. They are diffuse. They are breathing clouds of glowing gas so thin that their outer reaches would barely register as anything at all, shedding themselves slowly into space, pulsing gently over the years. The most enormous objects in the sky are also among the gentlest, the most loosely held, the least solid. And it is onto the very largest of these soft-breathing giants that we now, finally, step. The summit is just above us. There is a quiet beauty in the boiling surfaces of these stars that rewards a longer look because it overturns how we usually picture the largest objects in the sky. We imagine the great stars as fixed and solid, vast, unchanging monuments hanging in the dark. The truth is almost the opposite. A red supergiant is loosely held, soft-edged, and forever in motion, more like a slow storm than a stone. Its outer gas is so far from the dense core, so thinly spread, that the star can barely hold on to it, and it drifts steadily away into space in a constant outflowing wind. The star is always, gently, losing itself. The churning of the surface is on a scale that matches the rest of the strangeness. On the Sun, the rising and sinking cells of gas are small and countless, the whole surface finely simmering. On a red supergiant, the same churning is gathered into only a few colossal cells, each one larger across than the orbit of a planet, each one rising, spilling its heat, cooling, and sinking back over months, and years. As these enormous cells turn over, the star brightens and dims and shifts in shape, swelling slightly and contracting, never holding a single steady size. It pulses. It breathes. Watched across years, it is visibly restless, a living, shifting thing rather than a fixed lamp. This is the deep reason the largest stars resist being measured. When you ask for the width of such a star, you are asking for the edge of something that has no firm edge and will not hold still. The loosely bound outer gas swells and sags. The great convective cells rise and fall. The shed material wraps the star in shifting veils of dust. Measure it at one moment, in one color of light, and you find one answer. Measure it again later, in another color, and you find another, and both are honestly true, because the star itself has changed in between. We are not weighing a marble. We are trying to draw a line around a breathing red tide, and the tide will not stop moving long enough to be drawn. There is something to rest in here, in the realization that the most enormous things in the sky are also among the gentlest and least solid, soft, glowing clouds, shedding themselves slowly into the dark. There is a way of feeling the boiling surface that brings it close, despite its vastness. Imagine standing, impossibly, somewhere above the surface of a great red supergiant, watching it across years. You would not see a fixed sphere. You would see something more like a slow, glowing weather, enormous bright regions rising and swelling, where hot gas wells up from below, then dimming and sinking as that gas cools, vast dark lanes opening and closing across the face of the star. It would brighten and fade over months and years as these titanic cells turned over, a single one of them larger than the orbit of a planet. The star would seem to breathe, slowly, hugely, never holding the same face twice. And around it you would see the veils it has shed, clouds and shells of dust and gas cast off into the surrounding space, glowing faintly in the star's red light, softening and blurring its already uncertain edge. The supergiant would not sit cleanly in the dark. It would fade into a haze of its own making, a great soft star wrapped in the slow exhalation of its own outer layers. This is the truth behind every clean number we assign to such a star. The number is a single still frame, drawn from a slow, glowing, shifting, breathing thing that has no firm edge and will not hold its shape. There is peace in accepting that, in letting the largest stars be soft and uncertain rather than fixed and sharp. The summit and the largest known stars. Here we are, at the top of the ladder, the place this whole climb has been rising toward. These are the stars so large that the numbers stop feeling real, the red hypergiants and the most extreme red supergiants, the answer the question has been reaching for. We will not rush through them. We will walk among them slowly, one at a time, the way you would move through a quiet gallery of enormous, gentle things. First, what a hypergiant is. The hypergiants are the rarest and most extreme of the luminous stars, enormous, unstable, losing mass at tremendous rates, living right at the edge of what a star is even able to be. There are only a small number of them known in the entire galaxy, a handful of objects pressed against the upper limit of size and brightness. They are not common. They are the rarest kind of star there is, and the largest. The very largest are the cool red hypergiants and the most extreme red supergiants, swollen to 1,000 times the width of the Sun, and in some cases to over 1,500 times. At these sizes, the comparisons begin to lose their grip. 1,000 suns laid edge to edge across a single star. 1,500. The mind states the number and then quietly lets go of it, and that letting go is itself part of the experience. There is a red hypergiant in a southern constellation, long famous as one of the largest stars ever measured, that sits somewhere around 1,400 to 1,500 times the width of the Sun. It is wrapped in a complex, glowing nebula of material it has thrown off across the ages, and it is shrinking and changing even now, even as it is studied, a star slowly dismantling itself in plain view. There is a red supergiant buried deep in a rich cloud of stars in the summer sky that has been estimated, in some measurements, at around 1,500 or more times the width of the Sun, placing it among the very largest stars known anywhere. Its distance is uncertain, and so its exact size and its claim to the crown are uncertain along with it. There is another red supergiant, embedded in a massive and distant gathering of stars that has been measured in some studies at over 2,000 times the width of the Sun, a figure so vast that, set in the Sun's place, its surface would reach far beyond the orbit of the ringed planet, swallowing nearly the entire planetary solar system. Whether that figure holds depends entirely on its distance, which is genuinely hard to pin down, and so it remains a contender rather than a certainty. And there is a red supergiant in a small companion galaxy of our own, long considered one of the largest stars beyond the Milky Way, that has more recently been looked at with sharper eyes. The newer observations suggest it may in fact be somewhat smaller than once believed, and that it sits inside a flattened cloud of surrounding dust that fooled the earlier measurements into reading it as larger. It is a perfect example of how these crowns are won and then quietly revised. Several more red supergiants, scattered through the northern constellations, buried in dense clusters, spread across the galaxy, all cluster in the same enormous range, roughly 1,000 to 1,500 times the width of the Sun. And this is the quiet, beautiful truth at the summit. The top of the ladder is not a single sharp peak with one king standing on it. It is a small, high plateau, a gathering of comparably vast stars, all pressed up against the same upper limit, and which one stands tallest depends on whose distance measurement you trust in any given year. So the honest answer to the question, how big is the largest star, is not a single name. The largest known stars are this small group of red supergiants and hypergiants, all roughly 1,000 to 1,500 or more times the width of the Sun, and the crown moves gently among them as our measurements sharpen and shift. There is no tidy winner. There is a plateau of giants, breathing and shedding and slowly changing, far away in the dark, and that is somehow far more wonderful than a single fixed answer would have been. Let us walk the summit gallery a little more slowly, because these stars deserve to be met one at a time, and because there is more to understand about why their crowns shift. Each of the largest known stars has, at some point, been called the largest of all, and each has at some point yielded that title to another, not because the star changed, but because our knowledge of its distance did. This is the strange and gentle truth of the summit. The ranking is written not only in the stars, but in our measurements of them, and our measurements keep improving. The red hypergiant in the southern sky, wrapped in its glowing nebula of cast-off material, is a star in the visible act of unmaking itself, shedding matter so prodigiously that it has built a complex shell of its own substance around it. Stars like this do not hold steady. They pulse and shudder, brightening and dimming, growing and shrinking, and over the long span of their final age they may shrink overall as they shed their outer layers into space. To measure such a star is to catch a single frame of a slow and ongoing transformation. The number we write down is true only for the moment we wrote it. The red supergiant, once thought to be among the largest beyond our own galaxy, is a particularly gentle lesson in humility. For a long time it was believed to be one of the most enormous stars known, an object of truly staggering width. But sharper eyes, looking more carefully, found that it sits within a flattened cloud of surrounding dust, and that this dust had confused the earlier measurements, making the star red as larger than it truly is. The newer estimates bring it down somewhat from its former size. The star did not shrink. Our understanding sharpened, and the crown slipped from its head. This happens, quietly, again and again, all across the summit. And so the gallery is best understood not as a ranking, but as a gathering, a small, high plateau of comparably enormous stars, each one around 1,000 to 1,500 times the width of the Sun, some perhaps larger still if their distances prove greater than we think, some smaller if their dust has fooled us. The title of largest moves gently among them year by year as we look again and measure better. There is no single fixed king of the stars, only this quiet company of giants, breathing and shedding and slowly changing, far away in the dark. And that, when you sit with it, is a more wonderful answer than any single name could be. The universe does not give us a winner. It gives us a plateau of giants and an invitation to keep looking. It is worth saying plainly why these particular stars, the cool red ones, hold the record for width rather than the hot blue giants we admired earlier. It comes back to temperature and the swelling of old age. A hot star is compact, its gas drawn close and fierce. To grow truly vast, a star must cool, its outer layers spreading thin and reddening as they expand across an ever greater volume. Only the cool red stars, in the late swelling of their lives, open wide enough to reach the summit of width. The blue giants, for all their brilliance and mass, never grow so large, because to grow so large a star must first cool, and to cool is to redden. So the widest stars are, necessarily, red. The summit of size is a red summit, glowing soft and deep. The color of stars in their old age opened to their fullest. And the same coolness that lets them grow so wide also makes them so soft, so loosely held, so prone to shedding themselves into the dark. The largest stars are large because they are cool and old and swollen, and being cool and old and swollen, they are also gentle, diffuse, and impermanent. Their size and their softness are the same fact seen from two sides. They could not be vast without being thin, could not be thin without being unstable, could not be unstable without slowly unmaking themselves. The crown of largeness is also a kind of slow farewell. The biggest stars in the sky are, every one of them, in the long act of letting go. The scale made felt. Numbers like 1,000 or 1,500 times the width of the Sun are easy to say and almost impossible to feel. So let us slow down and translate them into something the mind can hold, gently, before we let them go. Take one of these stars, about 1,500 times the width of the Sun, and imagine setting it where the Sun is now, at the center of our solar system. Its surface would not stop at the inner planets. It would swallow the orbit of the innermost world, and the next, and our own, and the red world, beyond us. It would engulf the entire asteroid belt. And it would reach outward still, toward, and in the largest estimates past, the orbit of the great banded giant. The whole inner solar system, every world we think of as near, would lie entirely inside the star, buried somewhere within its thin red glow. The Sun, in this picture, would be a single, invisible point lost deep at the very center. Remember the light that crosses the Sun in a few seconds. To cross the face of one of these largest stars, that same light would need hours. A beam beginning at one edge would travel and still be journeying across the star long after it set out. and the passenger jet that needed 6 months of continuous flight to circle the sun once. To circle one of these giants, that same jet, never stopping, would need thousands of years. It would take longer than all of recorded human history for the plane to make a single lap. Here is perhaps the gentlest image of all. If the sun were shrunk to a single grain of sand, then one of the largest hypergiants, shrunk by the very same amount, would be the size of a large beach ball. A grain of sand and a beach ball. That is the gap we have climbed tonight. And yet, and this is the strangest part, that enormous beach ball of a star would weigh only a little more than a small handful of the original sand grains. All that size and so little extra matter because the star's material is spread so impossibly ghostly thin. For despite their staggering width, these largest stars contain only perhaps 10 to 40 times the mass of the Sun, not thousands. A few dozen suns worth of matter, opened outward across a volume so vast that the average density falls below that of the air we breathe, and in their outer layers, below the best vacuum that can be made in any laboratory on Earth. To drift through the outer reaches of such a star, if such a thing were somehow possible, would be to move through a warm, dim, nearly empty red fog, with the dense, bright core impossibly far below, out of sight, out of reach. So the largest stars in the universe are, in a sense, mostly glowing emptiness. Vast beyond picturing, and yet thin, soft, and light for their size. They are not dense monuments. They are immense, gentle clouds of faint red light, breathing slowly in the dark. We have reached the top of the ladder of width. But there is one more champion to meet, a different kind of largeness entirely, and it lives somewhere else on the slope. The scale of these stars is worth dwelling on from more than one angle, because no single comparison can carry it alone, and because dwelling on it slowly is its own kind of rest. We said that one of the largest stars, set where the Sun is, would swallow the inner solar system and reach toward the orbit of the great banded giant. Sit with what that truly means. Every world we think of as part of our own neighborhood, every familiar orbit, the whole region the Sun warms, would lie buried inside a single star, lost somewhere within its thin red glow, with the Sun itself reduced to an invisible point at the very center. One star, where an entire planetary system now turns. Try the comparison of time, too, because time makes the size felt in a different way. Light is the fastest thing there is, crossing the distance from the Sun to us in 8 minutes, crossing the Sun itself in a few seconds. To cross the face of one of the largest stars, that same light would travel for hours, beginning at one rim and journeying on and on before reaching the other side. And the slow passenger jet that needed half a year to circle the Sun would need not months, but many thousands of years to circle one of these giants, a journey longer than all of human history, simply to make a single loop around one star. These are not numbers the mind can truly hold, but the mind does not need to hold them. It only needs to feel, gently, how far we have climbed. And then there is the strangeness of the thinness, which is perhaps the most peaceful image of all. For all their staggering width, these stars hold only a few dozen suns worth of matter, opened out across a volume so vast that the gas grows thinner than air, and in the outermost layers, thinner than the emptiest vacuum we can make in any laboratory. If you could somehow drift inward through the outer reaches of such a star, you would move at first through what felt like little more than a warm, dim red haze, a glowing fog so tenuous it would hardly seem to be a star at all, with the dense, bright heart of it impossibly far below and out of sight. The largest stars in the universe are, in their outer reaches, closer to a colored emptiness than to anything solid. vast beyond picturing, and yet soft, thin, and gentle. There is something to rest in there, in the thought that even the most enormous things in the sky are mostly glowing space. There is one more way to feel the scale, and it is perhaps the kindest, because it folds the enormous back into the gentle. We have spoken of these stars swallowing the orbits of planets, of light taking hours to cross them, of jets needing thousands of years to circle them. These are true, and they are staggering, and the mind cannot really hold them. But here is the softer truth beneath the staggering one. For all that size, the largest star is still only a single point of light in the night sky, no different to the unaided eye than any other star. You could look straight at one of the largest stars in the universe and see only a quiet point, indistinguishable from its neighbors, giving no sign of the enormity it holds. There is something restful in that. The greatest stars do not announce themselves. They hang in the sky as quiet as any other, their vastness hidden by distance, their fierceness softened to a gentle point. We know how enormous they are, only through patient looking and careful measuring, not through anything the eye alone could tell. And so the night sky, for all that it contains these monstrous, magnificent stars, remains calm and quiet and even, a scattering of soft points across the dark. The enormity is real, but it is folded into gentleness, hidden inside the stillness of a distant star. The largest things in the sky look, to us, as peaceful as the smallest. The other champion, the most massive stars. At the start of the climb we set a quiet trap, and now is the moment it gently springs. The largest stars by width, the red hypergiants we have just walked among, are not the heaviest stars in the universe. The heaviest stars are a different gallery entirely, and they look nothing like the soft red giants of the summit. To meet them, we step off the ladder of width and onto the ladder of mass. The most massive stars known hold somewhere around 150 times the mass of the Sun, and in a few cases, perhaps over 200 times. That is a tremendous amount of matter gathered into a single star. They are blindingly hot, glowing fierce blue-white, and they pour out their light in floods, shining millions of times as brightly as the Sun. In luminosity, they are the true monarchs of the stellar world, the brightest individual stars that exist anywhere. And yet, in width, they are far smaller than the red hypergiants we just left behind. One of these most massive stars might be only a few tens of times the width of the Sun, not 1,000. All that enormous mass is packed into a relatively compact, ferociously dense, brilliant ball, blazing white-hot. They are heavy, not wide. Where the red hypergiant is vast and thin and cool, the massive blue monster is concentrated and dense and searingly hot. They are opposites in nearly every way except their rarity. One famous example sits at the very heart of a dense, crowded cluster of stars in a neighboring galaxy, among the most massive and most luminous stars known anywhere. It blazes with the light of millions of suns, and yet its body is only a few dozen times the width of the Sun, the exact opposite of the diffuse red giants. Another, a tremendously massive and violently unstable star in our own galaxy, is shrouded in a great dumbbell-shaped cloud of gas that it blew off in an enormous outburst long ago. It is one of the most luminous stars known, restless and eruptive, and almost certainly bound for a spectacular end. And here the trap closes completely. The widest star and the heaviest star are not the same object, and, more than that, they could not possibly be the same object. The very massive stars are too hot and too furious to swell into the cool, bloated, gentle shapes of the red hypergiants. If one of them tried, the sheer force of its own radiation would tear its outer layers away long before it could grow so wide. Width belongs to the cool, aging red giants, spread thin and soft. Mass belongs to the hot, blue, blazing monsters, concentrated and fierce. The universe keeps these two records in two entirely separate hands, and it will not let a single star hold both. So when someone asks for the largest star, the honest reply is another gentle question. Do you mean the widest or the heaviest? Because the answer changes completely depending on which you choose, and neither one is wrong. The cosmos is large enough and strange enough to have more than one kind of greatest. The most massive stars deserve their own slow consideration, because they complete the picture and resolve the puzzle the whole night has been circling. We have climbed the ladder of width to its summit, among the soft, cool, vast, red hypergiants. The most massive stars stand on a different ladder entirely, the ladder of weight, and at its top, they look nothing like the giants we just left. They are compact and dense and searingly hot, blazing blue-white, holding well over 100 times the sun's matter in a body only a few tens of times its width. They are not vast. They are concentrated. All that mass is gathered close, and it burns with a ferocity that the gentle red giants never approach. The brilliance of these stars is almost beyond reckoning. The most luminous of them pour out the light of millions of suns, so much energy that the pressure of their own light pushes outward against their gravity, straining at the very limit of what holds a star together. They are restless and unstable, prone to great eruptions, casting off shells and clouds of gas in violent outbursts that wrap them in glowing veils. They live fast, only a few million years, and they are bound for the most spectacular endings of all, collapsing and scattering their substance across vast reaches of space when their fire finally fails. And here, at last, the puzzle of the night resolves completely. The widest star and the heaviest star are not the same, and the reason runs deep. A star as massive as these could never swell into the cool, bloated, gentle shape of a red hypergiant without destroying itself, because the sheer force of its radiation would strip its outer layers away long before it could grow so wide. Width belongs to the cool, aging red giants. Their thin gas spreads soft across enormous volumes. Mass belongs to the hot, blue, blazing monsters, their matter gathered fierce and close. The cosmos holds these two records in two separate hands, and it will not let one star grasp both at once. So when we ask which star is the largest, we are really asking which kind of largeness we mean, and the honest answer holds both. The widest are the soft red giants of the summit. The heaviest are the fierce blue monsters of a different peak. Both are true, and the universe is grand enough to crown them separately. We should sit, for a moment, with how rare both kinds of champion truly are, because rarity is part of their wonder. The most massive stars, the blazing blue monsters, are vanishingly few. For every one of them, the galaxy holds many millions of ordinary stars and countless small red dwarfs. They are born rarely, they live only briefly, and so at any given moment, only a small number exist anywhere in a galaxy. The same is true of the largest red hypergiants, the champions of width. They are among the rarest stars there are, a mere handful known across the whole reach of our galaxy, each one pressed against the upper limit of size and lingering there only for the brief final chapter of its life. So both summits, the summit of mass and the summit of width, are sparsely peopled places, visited by only a few stars, and only for a little while. The cosmos does not make many of its greatest stars, and it does not keep them long. This is part of why finding and measuring them is so difficult, and why their crowns shift so readily. We are studying a small number of rare, brief, distant, shifting objects, each one pressed against the edge of what a star can be. That we can say anything at all about which is the largest is remarkable. That the answer keeps gently changing is only fitting. The greatest stars are rare and fleeting and far, and they wear their crowns lightly, passing them one to another as we look again. The ceilings of the universe and the quiet reflection. A natural question rises here, near the top, and answering it gently deepens everything we have seen. Why is there a top at all? Why isn't there a star 1,000,000 times the width of the sun, or 1,000 times its mass? Why does the ladder simply end? And the answer is that the universe sets ceilings, quiet but firm, and the largest stars are pressed right against them. There is a ceiling en masse. Above a certain amount, a star's own radiation pushes outward so fiercely that it blows away any further material trying to fall in. The star's light becomes a wind, and that wind prevents the star from gathering any more matter. There is a balance point where the outward push of light exactly equals the inward pull of gravity, and that balance sets a rough upper limit on how heavy a star can become. The most massive stars sit right at this edge, violently unstable, shedding matter in great gusts, flickering and erupting, living fast and ending soon. There is also a ceiling on width. As a star swells and cools, it approaches a boundary beyond which it cannot stay stable. Its outer layers grow so loosely bound that they begin to pulse and shudder and lift away, rather than expanding any further. The largest red supergiants and hypergiants sit right against this wall. That is precisely why they all cluster in the same size range, around 1,000 to 1,500 times the width of the sun, rather than ranging upward without end. They have reached the physical limit for a stable, cool star. They cannot grow any wider without simply shedding themselves into the dark. A hypergiant is, in truth, a star caught in the slow act of dismantling itself, which is part of why so few of them exist at any one moment. And there is one more reason the summit shifts and wavers, which is worth holding gently as we begin to descend. The exact size of the largest star is not a fixed fact, and it was never going to be. Distance is the great uncertainty. A star's measured width depends directly on how far away we believe it to be, and a small change in the distance becomes a large change in the size. The largest stars are far away and difficult to range. Dust wraps them, dimming and reddening their light until sharper eyes can see through it. They pulse and swell and contract genuinely over months and years. And their edges are soft, fading into space with no clean line to measure. So the same star, measured twice, can honestly give two different answers, and the crown can pass from one giant to another with nothing more than a better measurement. There is a deep peace in this, if you let it settle. The cosmos does not hand us a final number and close the book. It hands us an ongoing wonder, a question it keeps gently reopening, a summit that breathes and shifts and rewards us for looking again. And the stars at that summit are themselves brief and soft and impermanent. The most luminous live only a few million years, a flicker against the long ages, building heavier and heavier elements in their cores until they can hold themselves up no longer, and then collapsing and scattering their substance back into space. From that scattered material, dust and gas and newly forged elements, new stars and new worlds are slowly born. The largest stars are the furnaces that forge the raw substance of everything that comes after, including the calcium in bone and the iron in blood. Their endings seed beginnings. And what they leave behind, at the very last, is one of the dense little ghosts from the bottom of the ladder, a neutron star or a black hole, the widest things in the universe folding down into some of the smallest. The ladder closes its great circle. And so we leave the largest stars where they have always been, turning slowly in the far dark. So wide that light needs hours to cross them. So thin they are little more than glowing air. So brief that they will scatter themselves back into the night before the galaxy has finished a single turn. No one needs to crown them for them to keep shining. Whatever the largest star turns out to be next year, it will still be out there, vast and gentle, and indifferent to whether we have named it correctly, doing the only thing it has ever done, which is to burn quietly in the dark. It does not need to be measured to keep shining. And neither, tonight, do you. Let the scale settle softly over you. Let your breathing slow. Let the space behind your eyes grow quiet and wide. Sleep well, and good night. There is a great deal of quiet wisdom folded into the ceilings the universe sets, and it is worth unfolding gently as we begin our descent. We might expect that, given enough time and material, a star could grow without limit, larger and larger, heavier and heavier, forever. But the cosmos does not work this way. It draws lines, soft but firm, beyond which a stable star cannot go, and the largest stars we find are not freaks of unlimited growth. They are objects pressed right up against those lines, sitting at the very edge of the possible. There is order beneath the wildness, a quiet set of rules that decides how large a thing of light and gas may be. The line on mass is drawn by light itself. As a star grows heavier, it grows vastly brighter, and at the greatest masses, the outward pressure of all that light becomes so strong that it blows away any further matter trying to join the star. The light becomes a wind, and the wind slams the door. A star cannot easily grow heavier than the point where its own brilliance begins to push its building material back out into space. The line on width is drawn by stability. As a cool star swells, its outer layers grow ever more loosely held, until at last they begin to pulse and lift away rather than expand any further, and the star can grow no wider without simply shedding itself into the dark. The largest red hypergiants sit exactly at this edge, which is precisely why they all gather in the same size range, rather than ranging upward without end. They have reached the wall, and the wall holds. So the summit of the ladder is not an accident or a coincidence. It is set by the deep physics of light and gravity and gas, the same forces that hold a star together in the first place. There is no star 1,000,000 times the sun's width, because such a thing could not hold itself together for an instant. The largest stars we will ever find are pressed against the ceiling the universe allows, and that ceiling is itself a kind of gentle order, a quiet law beneath the apparent wildness of the cosmos. Even the most enormous things obey the rules. Even the giants have a limit, set not by chance, but by the nature of things. And as we come down at last from the summit, it is worth gathering the whole climb into a single, soft thought. We began at the bottom, among the small, dim, patient red dwarfs and the dense little ghosts of dead stars. We climbed through the steady middle, where the sun lives, and up into the swelling giants, and higher into the supergiants, with their boiling, shifting faces, and at last onto the high plateau of the largest known stars, the soft red hypergiants, pressed against the edge of the possible. We saw that the heaviest stars are not the widest, that size and mass are two different kinds of greatness, and that the cosmos keeps a separate crown for each. We saw that the largest stars are mostly glowing emptiness, vast and thin and gentle, and that they are brief, shedding themselves slowly back into the dark from which new stars and worlds are made. And we saw that the answer to the question we began with, how big is the largest star, is not a single fixed number, but an ongoing wonder, a crown that passes gently from giant to giant as we look again and measure better.